Hey guys, so I've been trying to actually upload this video for a little while, but I keep having like really blurry results and stuff. So hopefully, I've actually taken it a couple times. Hopefully this will be clear, writing in Sharpie, and hopefully I won't have any problems with this video. And this video is on limits. And what are limits, and why are they important? Let's start with why are they important. Limits are important because they're basically the fundamental building blocks for all of calculus, and I mean it gets a lot more advanced than what we're going to do in this video, but it allows us to do all the cool stuff that we get to do with calculus. Now, what is a limit? Limit, whenever it's pretty much seen in this notation, the limit as x approaches a of f of x equals L. And when you're doing like a limit problem or you're solving a limit, you're solving for L. So L is the limit. And like pretty much anything in mathematics, this notation right here might look kind of daunting or intimidating, but really when you break it down into just what it's saying in English, we see that it's not that crazy. Although it's a little difficult to explain exactly what this is. It's basically, we use limits to find an approximation as we get closer and closer to something. And what does that mean? Well, that might be kind of difficult to understand without a visual, so let's make a visual. Okay, we have my little graph right, have my little graph right here, this is y, or f of x, whatever you want to call it. And this right here is going to be my graph, f of x equals x, right here. So, let's say I have this point 1, so x equals 1 right here, and obviously, let's see, go up here, y equals 1. If I want to find out, as my x value is getting closer and closer to 1 from either side, as I get closer this way, if my x is like 0.5, or if my x is like 0.9, getting closer and closer, what is my y value getting closer and closer to? So what is this approaching? What is my function approaching? And obviously we can kind of tell that as x is getting closer to 1, our y value is going to be getting closer to 1 over here. And that's just kind of because we know that the graph y equals x for x equals 1, y is equal to 1. That's kind of obvious. But I want to show this problem because it's important to see how you do a limit problem, sort of like just the process on an easy problem, so when we get to kind of a little different problems, we can still know how to do them. So for this problem, how we do is the limit as x approaches a, and in this case a is 1, we want to find as x is getting closer and closer to 1, not quite at 1, but just getting really close to it, of f of x, what is the L? And we know, because I defined it, that f of x equals x. So I can substitute in here the limit as x approaches 1 of x. Now what does that equal? And basically the way we do this is we just substitute in our a value, or in this case 1, and we put it in wherever we see our variable x, whatever the variable that is approaching something. In this case it's x, and it's approaching 1, we just plug it in, and that's pretty simple, and we get 1 is our limit. So if that's so simple, and calculus is kind of, I don't know, it's kind of known for being this big subject, and it takes us so many years to be able to get the prerequisites to get into calculus. Why is calculus considered so difficult, and how can this be the building block of that? Well, first we're going to move on to a problem that's still not very difficult, but I think gets us into a little more interesting properties of what we can do with something like a limit. And we're going to use a similar graph, but not quite the same function. So this is 1, this is 2. Okay, so I'm going to give you the name of this function, and then we'll talk a little bit more. This is going to be... Well, actually, first let's talk about what this is. What is this that I just drew? So this is a line with what we call a point discontinuity. Point discontinuity, and what does that mean? Alright, a point discontinuity is when you have some curve, in this case we just have a straight line, some curve, and at one point on the graph, for a singular point, it's undefined. There's no y value. in the equation. And how does that happen? Well, when we get something undefined, you're probably more used to it being like 5 over 0 is undefined. Hopefully you've learned that. And the reason for that is because 0 represents nothing. And 5 divided by 0 is saying how much nothing can you fit into 5. And that's just unlimited. It's like infinity. So this is an undefined value. So similarly, we're saying over here, we have some value that we just can't define at x equals 2. So I'm going to give you the equation of this graph, and then I'll kind of explain why that equation equals this graph, and then we'll work the limit. So the equation of this is f of x equals, I'm going to start with x minus 2 in the denominator of my equation, and that's because when x equals 2, I want it to be undefined. Just like in this problem, I want it to be equal to 0 in the denominator. Then I'm going to also put x minus 2 in the numerator and multiply that by x. Now, why did I do these two things? Well, I put x minus 2 in the numerator because I want my graph to look like x still. Because this looks like, just like in this problem, y equals x. I want it to look like y equals x with the characteristic that it's undefined at x equals 2. And when I write it like this, you can kind of see, hopefully, you know how to do fractions, that these two values cross out, and we're just left with x. And that's why I put x minus 2 in the numerator, to cross out with this x minus 2 in the denominator. And then I put this x here, because I knew that when I cross these values out, this would be my function with the characteristic of the function being undefined at 2. So, f of x, let's continue over here. F of x equals, let's do x times x minus 2 all over x minus 2. That is this function right here. Now let's say I want to find what y would be if I did have a function here. And I know I just told you that it's equal to x, but again, for the sake of just kind of working through a problem, this is kind of interesting because I want to know if there was a defined value for x here, what would it be? So another way we can say it is, as I'm getting closer and closer to 2 from either side again, what is my y value getting closer and closer to? What am I approaching? So the way we do this problem is going to be very similar. The limit as x approaches 2 of f of x, and I know that f of x is equal to, we already talked about this a lot, x times x minus 2 over x minus 2. Sweet, so we just plug in the value right back in like we did in the other problems, right? And then we'll get 2 times 2 minus 2, that's 0, all over 0. And this is where we kind of have to do something a little tricky because, like we've already talked about, when something is divided by 0, it's undefined, so then we get an undefined limit. And in this case, our limit is not undefined, and as we'll see in a sec. So the way we fix this is we do what I already did when I was kind of showing you what the function, why this graph is equal to this function, is we cancel out these values when we're evaluating our limit. Limit as x approaches 2 of x minus 2 times x over x minus 2. We cross these values out, and we just take, let me get a new piece of paper. No, I got room. We take the limit as x approaches 2 of x, and that's obviously going to be equal to 2, using the same method we did in this problem. So what we can say because of that is, for this function, right here, as x gets closer and closer to 2, my y value is also getting closer and closer to this 2. Alright, so there's not always going to be quite this simple, because even if we have, I'm going to show you guys a different kind of discontinuity that we have, and that we use limits for. It's called jump discontinuity. Okay, so if I have, let's see, like this 1, 2, it's going to be negative 1, we'll go. I hope you guys can see all this because I would suck if I have to shoot this video again. Alright, so this is my function f of x. I don't have a name for this one, but so this is our x-axis, this is our y-axis. So I have some function f of x, and it comes up as over here, and it doesn't quite get to 1. There's it's undefined here, but then up here it continues. So this is what we call, it's still not continuous. This is called jump discontinuity, and I'm not going to write discontinuity again. Okay, it's called jump discontinuity because we still have a value for every place on the curve. So at -1, even though it's not continuous here, up here, this is a filled-in circle representing that at -1 we still have some value. But if we were to just say, what is the limit, and this is -1, mind you, what is the limit as x approaches -1 of f of x? Well, at first we might say, okay, well, if we're going to follow it up like this, as it's getting closer and closer, it would be 1. But if we came from over here, and as we got closer to -1 from this side, we follow here, we would get 2. So what do? Well, there's actually no limit. It's kind of undefined in a different way than our other problem was. And the way, if we wanted to find the limit of this or the limit of that, there's notations for saying which one we want to find. And the way we're going to do that is the limit as x approaches -1 from the left. So that means I'm coming from the left towards x, so I'm coming this way, getting closer and closer to -1. What am I approaching? And it's easy to remember that because the negative sign you can just think of as you're coming from the negative axis, so it's going to be coming from the left. And the limit is we can see y is getting closer and closer to 1, or that's what I was supposed to have drawn. So there we go. The limit as x approaches -1 from the right, we indicate that with a little positive sign, coming from the positive axis towards -1, we can see that our y value is approaching 2. Let's see what other, okay. The last kind of limits I want to talk to you about are asymptotes. So let me just get another good graph over here. And this is going to be, let's make this y equals 1. Have some asymptote of a graph over here. And it's going to go like that. Okay. Now, so we have an asymptote here, which means x is just, you might have heard someone describe it this way, x is going to get closer and closer to this but never touch it. And that's perfect for something like a limit, because in a limit we're getting closer and closer to some value. What is the limit as we get closer to it? So, this is f of x, and we want to say the limit as x approaches infinity, so as we're just going on forever, of f of x. In this problem, it's just going to be a number. It's going to be 1, because as x is going on and on forever, it's getting closer and closer to this asymptote. And that's kind of how limits apply to asymptotes. And I guess one last thing we can go over is sometimes there really is no limit of a problem. If we have this right here, the limit as x is approaching infinity over here, it's just going to be infinity on the y-axis too. This is some third-degree polynomial, this function right here, f of x. And there's really just not any limit going this way or this way. You could say that the limit as x approaches infinity is infinity, but really you would just say no limit or undefined. The last thing I want to talk about, going back to this problem, is a lot of times in limit problems, you're going to have to do something where you simplify what your original function is like this. So that's just important to keep in mind. Alright, now that we've got some basics, we can start doing some cool stuff in the next video, so can't wait to see you guys there.